were looking at our Arrhenius equations and collision theory. We already talked about collision frequency, temperature effects, and steric effects. When we think about like the activation barrier, it's a lot like this little picture of going over a mountain pass. This is a nice clear picture where we have A and B reactants going to products. We have our activation energy in the forward direction labeled and in the reverse direction labeled. And then you see that double dagger symbol up there, the AB transition state, as well as H is the enthalpy, delta H. So the progress of reaction can be a little bit abstract to think about, but the number of collisions is proportional to that exponential. So there's like the total number of collisions that happen, and then the proportion of them that are above that activation energy at that given temperature. All right, so here's a couple numbers, right? And this graph is really nice, showing those filled in areas for the fraction of molecules that have that energy at a given temperature. The high activation energy is a tall barrier, so that's going to be a slower reaction. If it's a lower activation energy, it'll be a low barrier and will be a smaller. And there's a couple questions in here. Draw a rough sketch. For this one, we're really looking at the activation energy. So the fastest rate is just going to depend on that 30 kilojoules per mole. But it's still, the actual observed rate is still much smaller than we would expect, and that's because of those steric effects. So this is basically just another animation showing the orientation effect. One of the other things I like about the lecture slides is I put a lot of time into putting numbers in there, so you get actual value amounts, right? So in the transition state, in this case, it's showing the hydroxide coming in and attacking that carbon and actually flipping the molecules, right? Releasing the bromine so that you get this inversion of that trigonal planar in the transition state. So it's like partially formed and partially broken. Okay, and this is the example we saw before with a bunch of values given. Yeah, let's go back to worksheets. Okay, so we have that K. What's K? Yeah, that rate constant, that's right. So it's times some factor, which is composed of both the collision frequency and the orientation factor, times that exponential that has the activation energy up in the exponent. So in order to get that into a linear form, we go ahead and take the natural log of both sides, got a y equals mx plus b. So we'll plot log k on the y-axis and 1 over t on the x-axis to get a linear fit. From there we can get the slope. So here's our slope calculated for us. What's the slope here from this equation? That equals minus EA over R. Right, so you can see from the equation, slope equals minus EA over R, and that equals this negative value, so it's going to come out positive. And we're going to use the value of R that has joules. So in all of our energy chapters, we use joules per mole Kelvin. In our gas law chapters, we use liter atmosphere per mole Kelvin. So you got to pick the right R. That equals minus EA, we're solving for 8.3145 joules, and then moles in Kelvin come up here.
Is that because we're trying to get the units to cancel? Is that why we use that constant?
Yes. We want our energies to come out in joules or kilojoules. All right, the kelvins cancel, that's joules per mole. That's times 10 to the 4. So I'm going to put that into kilojoules.
Do we just get rid of the oh yeah, they both sides have negative, so.
Yeah, both sides have the negative side. That's right. So you got to be so careful. I don't think we ever have a negative activation energy. I mean, that just doesn't make any sense, does it? All right, and that's actually 2 sig figs there. All right, so that's how we can get that activation energy from the Arrhenius equation, right? Yes, Arrhenius equation. We can take data at 2 different temperatures and we'll get 2 different rate constants. And if we subtract those, so I'm going to take this whole equation and subtract it from that one. Then on the left side, we have log of K2 minus log of K1. Those logs can bring the K's inside, so we end up with this expression. And then on the right side, notice that the log of A cancels out. So we could find what that factor, that frequency factor is, but we don't do anything with it. Just doesn't pan out to be that useful. You can find them in the literature, but if we just use 2 different measurements, we can compare temperatures and find rate constants at different temperatures, or we can find that activation energy from just 2 measurements of the rate constant at temperatures. So,
sorry, Professor, quick question. Why did we make the second temperature negative value? Where
the
we
temperature
have
has to be
T.
in Kelvin, so they all have to be positive. But I'm basically subtracting this equation from this equation.
So in the it's flipped on that example. It's the second minus the first equation.
Yeah.
Right?
Okay. So we do see it 2 ways. And where's my equation? I pulled out my equation sheet. The standard way that we write these equations typically has the T2 first. So here we have 1 minus 2, and it's because we put that negative sign in front. So when we have this equation, the 1-point equation, we have that negative sign out in front of the EA. So in order to keep that there, we just switch the order of the T's. The way it's written here is a little bit less conventional. It's usually minus EA over R, 1 over T2 minus 1 over T1. And that difference is that negative sign, flipping the order of the T's. So all of these, typically I memorize them. They're usually the one that's on the top in the log, the K2, goes with the first temperature, the T2. But it makes it a lot easier to calculate activation energies. You don't have to plot everything. You can just take this data at 2 points. So here we want to find the activation energy in kilojoules per mole. And then we've got K at 25 degrees and a K at 55 degrees. Remember, those always have to go into Kelvin. I'm just going to designate 1 to be 1 and 1 to be 2 and make sure they line up. It is useful to plug in your R values to make sure that you have your units correct. Yeah, 8.3145. Also, I suggest that you always complete this difference of inverses in a separate step and write down that value. That can be very, it's error prone.
Is it 104 kilojoules?
Oh, the final answer? Yeah. All right, set on that one.
For your temperatures, so you have it as 1 over T1 minus 1 over T2, is that correct? Or, yeah, 1 over T1 minus 1 over T2?
No, I let this one be T2, but I flipped them here. Right, so the first one goes with that one.
I was following the first equation. So the natural log K2 over K1 equals positive EA over R times T1 minus T2.
And that'll work. The only difference is that I have a negative sign here. So when you come out, you'll have a negative sign here instead of right here.
Yeah, that's true.
So either way it should work. It's really this algebraic issue with that negative sign. So let's do another one. So I'm going to use natural log of K2 over K1 equals EA over R 1 over T1 minus 1 over T2. So I'll use this one. So it's probably helpful to mark on your paper which one is which. So I think about that top K. The way that I have memorized it would be to have that be the first temperature with a negative sign here. But in your textbook, they're keeping it positive here with the top K matching the second temperature. Right, because this equals minus EA over R 1 over T2 minus 1 over T1. Okay, how does that look? All right, are you with me? We've got to take the exponent of that. What is negative? All right, and this equals K2, and that is a first order reaction. So those units are going to be seconds to the -1. So a couple of words. So I've been a little bit fast and loose with the significant figures. Do you remember significant figures from pH? How they go between the log and the concentration? Yeah, it's kind of a nuisance. When we're dealing with logs, it's usually good to keep some extra ones because it can make a big difference. So in this case, here we've got 3 significant figures inside the log. So that should mean that we're good to 3 decimal places after the log, right? I always get that mixed up, but I'm always thinking about the pH, because if we have a concentration that has 3 sig figs, then we get a pH that has 3 decimal places after the number, after the decimal place. All right, one more example.
Oh, we got to find out the temperature for this one. Oh boy.
Yeah, so this is really algebra, just algebra this way and that way. Oh, T1, the first one. So I plugged it into the other one, so I'm going to stick a negative sign there.
Okay.
Okay? I'm trying.
So if I don't have the negative sign, I gotta put the T2 at the back, right?
That's right. But I wanted the one that I'm solving for to come first. So if this temperature matches this K, then it has the negative sign. That's what I always look for. If you didn't have the negative sign, you would just flip the temperatures. Maybe if I just call that T2. Then the 4.61, this one would be K1, and then this one would be K2. And what have I got? 12508 Kelvin times 1 over T1 minus So be very methodical, of course, with your math here. 1 over T1.
Wait, Dr. Gibbons, you mean T2?
Yes, T2.
Wait, we solving for T2 the whole time, right? So you just mistaken writing T1.
Sure. You know, the designations are completely arbitrary.
Okay.
So as long as they match correctly, it's fine.
I got 330, but I got 604 degrees Kelvin.
$604?
Oh.
So you got 603.6 Kelvin?
I got 643.96.
Oh, you did? Okay.
Oh.
All right. Well, I've gotten both of those answers in the past, so we'll figure out we'll figure that out tomorrow when we start.
Okay.
But I wanted to point out that All right, so if you go to the lab day, under here, the lab manual pages are posted, and you can use those to do the Kinetics pre-lab quiz. Oh, I also posted some questions to kind of get discussion going on the forum. These are things that if you just try to answer them in your own words, or if you find something that doesn't make sense when you try to construct language to explain it, that's really where you get to the extent of your knowledge, and that can really help deepen what you're thinking about.
Next week's lab, the first lab, that should be in our lab notebook.
Yes, if you can
Okay.
put it in your lab notebook, that would be excellent. If you look at exam 1, I have an equation sheet posted. So that should help you know what I'm going to give you. Here's what it looks like. Yeah, so I don't think we're doing any of the delta G, delta S stuff. That's at the end of the quarter. Then those discussion questions would prepare you for conceptual type questions. This I get a different number right there. And then when I invert that,
Wait, Dr. Gibbons, I have another question.
okay.
So on example 1, how did you determine which one was K2 and which one was K1?
When you go up to example 1, I just picked one.
Or it can just be like absolutely random.
Yeah, it can. As long as you've got it connected to the correct position in the equation.